Hello, my name is PHYS Johnson, and this is Lab 3 Magnetic Field of a Bar Magnet. So first we're going to start with our introduction and some models used during this experiment in this lab. In this lab we're going to investigate the magnetic field of permanent dipole magnets. And the purpose of this lab is to extend our understanding of how magnetic fields work, and we're doing that by measuring the distance dependence of a bar magnet's magnetic field. And we're going to measure the field strength at different distances from the bar magnet. And then we're going to use the Biot-Savart law to model both the on and the off-axis magnetic fields. And then, of course, we're going to analyze the distance dependence of the magnetic field. And then we're going to compare the computational model that we're going to build in GlowScript to the experimental data that we observed. So some important formulas and concepts that we use. We, of course, have the Biot-Savart law that's used to find the magnetic field from an object. We have the off-axis magnetic dipole formula below that as well. We have this formula for distance dependence for bar magnet as given to us in the lab instructions. We can see through both of the formulas that we can make the assumption as distance increases, the strength of the magnetic field does in fact decrease. We can see this results through our lab. So just to give a quick and a brief walkthrough of how we conducted the experiment. First, we canceled the magnetic field of the Earth by setting it to 0. So we're going to adjust the ruler in the phone until it hits 0, and then once we do that, we're going to find the location of our magnetometer. Once we do that, we can calculate the distance from the magnet to the magnetometer sensor for multiple different values, and we're going to repeat the procedure from 20, a BX value of 20, 120, 170, and 220. We're going to do the same thing for off-axis, and we're going to be calculating our D perpendicular instead. So here's our experimental data. You can see the walkthrough on the right hand side, how I calculated my magnetic moment that will be used as an initial condition in our code. Basically, it's broken down into a formula. I take the E to remove the ln to get the K value. Once I get that, I can plug it into the K times R to the nth power. And then from there, we're going to set it equal to the off-axis, or I'm sorry, the on-axis dipole. And then we can calculate our magnetic moment from there. And at the bottom, we see our off-axis field data. We are given the Bx, the By, and the Bz that we observed from our experiment. A quick preview. On the left-hand side is our GlowScript model. We can see the visualization as well as the GlowScript result. As you can see between the experimental result and the GlowScript result, the results were not close to each other, unfortunately, but we can explain a lot of that variation through some errors that we will discuss later. But next, let's get into the code. So starting off here with our code, just like some initial conditions, we have the constant that is set on the 10 times 10 to the negative 7. Moving forward, we have the magnitude of the magnetic moment. We calculated that earlier in our presentation. This is where we're going to insert it, the 0.016. Next, we wrote the function for defining the magnetic field. Moving forward, we edited the B scale and the distance, both which are tuning parameters, so we're going to adjust those as needed. Moving down, we're going to calculate the B axis, the B for the 2 on axis, and then the B for the 4 perpendicular here. And then we calculate, of course, the R, and then from there we can plug it into our defined function right here. Then once we complete those, we're going to insert the D perpendicular that we calculated or we observed from our experiment. And then lastly, we're able to build the observation for the 45-degree angle. Then we're going to calculate the R, which is the distance between. And since it's on the origin, at the origin, it's just going to be the observation itself. Then we send it through our defined function again to get the final B at the 45-degree angle. And we have a magenta arrow to represent that. I'm going to run our code so we can see exactly how it looks. So we see we have the 2 on axis pointing with the magnet, and then we have the perpendicular pointing the opposite direction. And okay, finally for our findings and our conclusion, some potential errors. Of course, there's going to be the outside objects affecting our measurements. The lab asked for the readings to be done far from other electronics. It was done in the classroom, so our measurements may have been affected by the multiple computers, phones, smartwatches, etc. Also, just the incorrect location of the magnetometer. It is possible during our setup that we incorrectly found the location for the magnetometer, which is going to harm the validity of our data. Our observation that we found was that as the magnetometer moves closer to the magnet, the X component of the magnetic field does increase. Addressing our additional questions, what if you hadn't orientated your experiment to compensate for the magnetic north? If we didn't do that, if we didn't set up the meter stick to cancel up the magnetic north, the readings would have been inaccurate, as the Earth's magnetic field would influence our data. What if we were to stick two identical magnets together end to end and run the experiment again? If the two magnets were identical, our data would just double in its magnitude due to the presence of another magnet, just like the case with coils where N is incorporated into the formula.